Okay, before we actually begin our discussion on state machines, I want to talk to you about a particular kind of flip-flop, okay? Now this flip-flop here is referred to as a D-type flip-flop, okay? Now basically speaking, a flip-flop is really a memory device. Now I want to explain to you basically how this flip-flop actually works. Now it's got a D input, it's got a Q output. You always have a Q bar output available as well. Okay. The other input it's got, and these are just the basic inputs I'm showing you, the other input it's got is referred to as a clock input. Now in the case of the flip-flop, basically this Q output cannot change, will not change, unless you get a leading edge of the clock signal. So there, if you like, is a leading edge of that clock signal. So a clock can be viewed as a repetitive, a periodic type waveform such as that. And of course, when you're going from a 0 to a 1, that represents the leading edge of the clock. So what we're saying is that the Q will not change until you get the leading edge of the clock. Now, if D were, let's say, a 1 and Q were a 0, okay, Q will not change. But when you get that leading edge of the clock, then whatever is on D then becomes the new Q output. All right, so what we're going to do now is we're going to sort of go through a little truth table here to explain basically how this device really is operating. Now what I have to do here really is I have to define a couple of times. I have to define maybe a time here which I'm going to call T, and that is just as it were before the leading edge of the clock. And then I'm going to define another time here which I'll call T plus delta T, which is the time as it were just after you get the leading edge. So T is before the leading edge and T plus delta T is just after the edge. Alright, so let's put together this little truth table here. So what have we got? We're going to talk about the clock, okay? We're going to talk about the D input, and then we're just going to talk about Q, the value of Q before you get the clock edge, and then the value of Q just after you get that leading edge of the clock. And this type of flip-flop is called a leading edge triggered flip-flop. There are also falling edge triggered flip-flops available. All right, so we'll look at this truth table. Now let's supposing, for example, that D is a 0, okay, and we'll say that Q, all right, before the clock edge were a 0, okay? All right, now here comes that leading edge of the clock. There it is. The output Q, after you get the leading edge of the clock, that's Q at T plus delta T. Q won't change, okay, because D was a 0, so Q becomes Q after the edge is also a 0. So we didn't see any change there. All right, that's the first case. All right. Now let's look at the case that Q is a 0 before you get the leading edge of the clock, but now we've got D set to a 1. Okay, so there's D at a 1. All right, hasn't changed Q, but when you get this leading edge of the clock, okay, then Q will change and Q will become this D value, and so Q at T plus delta T, which is after you get the clock edge, Q will have gone to a 1. Okay, let's move on. Let's supposing now Q were a 1 before the clock edge, and let's say D were a 0. Here comes the clock edge. What's going to happen? Well, D is a 0, okay, clock comes along, Q then will become a 0 after you get the clock edge. All right, now let's look at the case, the last case here of our truth table, where maybe Q before the clock was a 1, D was a 1. I get the leading edge of the clock. I wouldn't expect Q to change. I would expect Q to become a 1 again. All right, so you need to understand how this D-type flip-flop is operating. It is an edge-triggered device. This Q output cannot change until you get a leading edge of the clock. Now what I'll do now is I'll show you a little timing diagram that will help further explain this. Okay, look, here what I'm doing is I'm showing you the clock waveform, all right? Now we know changes can only occur on the leading edge of the clock, so what I've indicated down here with these dotted lines of where those leading edges of clock are. All right, let's see if we can predict the behavior of this flip-flop then. Okay, so what we're saying here is that this leading edge of the clock, basically the input D was a 0, that leading edge of the clock there, and so the output Q would be a 0. So there is Q sitting at a 0. Now let's imagine that we change this D input. We make this D go to a 1, we hold it at 1 for a short period of time, and then we take it away again, and perhaps that's our waveform for D. Okay, what's going to happen to Q? Well, as I said to you, Q cannot change. We may have this change here occurring, but Q cannot change until you get the next leading edge of the clock, which is over here, and so Q remains at 0, like so. By the time you get to that next leading edge of the clock, what is the D input? Well, the D input is back down to a 0 again, and so whatever is on D then becomes the new Q output at that leading edge of the clock. So Q still remains at a 0 because D was back down to a 0 again. All right, let's continue. Supposing now we make D go to a 1 and we hold D at a 1 beyond the leading edge of the clock over here. All right, so what's going to happen to Q? Well, Q cannot rise up when D rises up because Q cannot change until you get the leading edge of the clock. So here's the leading edge of the clock. What is the D input at this point? The D input is a 1. So a 1 at the leading edge of the clock will now cause the Q output to go up to a 1 condition. Okay, so I hope that helps to further explain really how this flip-flop is really behaving with respect to the D input and the fact that changes can only occur when you get that leading edge of the clock. Now we use these flip-flops actually in our state machine, but look, before we begin to incorporate these, let's look at this traffic light example. So that's what I really want to do, is I want to look at really a traffic light example. Traffic light example. Okay, now let's look at this. Supposing my traffic light system is such that I have a road that goes in the north-south direction, And what we have is, let's say, like a pedestrian crossing that will cross that road. Okay, so basically it's a north-south direction road, and we have a pedestrian crossing, and let's say what we have over here is some kind of switch. We'll call this switch S. And if a person wants to cross the road, so you've got somebody here that wants to cross this road, what do? They press the switch. This will change the traffic lights for them to be able to cross the road. So the traffic lights should go from a green, basically, to a red. Now that's the system that we're really going to try to talk about. Okay? So let's look at what we've got here. We're going to come up with, if you like, an algorithm of what we want to do. Okay? Really, this is the creative part of our state machine design, is coming up with this algorithm of what you want your machine to actually do. Now, we're going to start off with something really very simple here to really develop, if you like, a design methodology. And once we understand that methodology, we can certainly come up with more complicated algorithms, and we'll be able to understand and more of the issues and concerns. All right, so we're going to start with something very simple. All right, so what we're going to say is, look, I've got a state here, and I'm going to represent a state, and we'll formalize this a little bit later on, but I'm going to represent a condition that we're in, as it were, by a rectangular box. Okay, and in this rectangular box, I'm going to put the conditions, if you like, of the road and of the pedestrian crossing. And so in the box, I'm going to say the road lights would be north-south lights would be green, okay, north-south green, and we'll signal to the people that simply says wait. All right, so it may be a light that comes up that would say wait. All right, so that's the condition that we would be in that particular state, if you like. All right, in this box, I'm only showing you really the active conditions, and so the active condition here is you've got the green light on for the traffic and you've got the white light on for the people. All right, now what we're going to do is we're going to use a diamond type shape here to represent, as it were, an input to this system, and this will be the switch input. So in other words, if nobody has come along to press this switch, we're going to say that the output of that switch then is basically a 0. And if it is 0, we want to stay in this condition, or in this state, if you like. If somebody has come along and they've pressed the switch, we'll say that that corresponds to a 1 condition, okay, which will move us to another state. And in this other state, we will have a new traffic light condition. And what we're going to do is going to change the lights here. And so we'll change the light condition now to north-south. We'll change it to a yellow light. But we'll still keep the wait sign on as far as the people are concerned. All right? Then we'll move to another state. In this other state, what we'll have here is north-south going to red. We'll still keep the people actually waiting at that point. And then in the next state, we'll keep north-south as red, and we'll let the people go across the road. And so what will light up is a go light for the people. And then when we come out of that state, we will go back all the way to the beginning again. Okay, so there is an algorithm, if you like, for a very simple traffic light system. Yes, it has problems. Yes, it's not going to be perfect. And really, it's not going to be practical. But we'll be able to use this to develop that methodology, and then we'll try to evolve this traffic light system into something that is actually realistic. Now, I'm saying that these are different conditions that this machine is going to be in. These will actually represent different states that the machine is in. Okay? The time you stay in a given state is really dependent upon the clock, and hopefully we'll see and understand that a little bit more as we get into this. Okay? All right, we need to have a way now of labeling those states. Okay? And we need a binary way of labeling the states. We've got 4 states, so I really need 2 binary digits, as it were, to uniquely describe these 4 separate conditions. So look, for want of better labels, I'm going to call this I'm going to say I've got AB as the binary variables, and I'm going to say that this state would be, for example, a 0, 0 state. I'm going to say this state could have an AB value of 0, 1. This state could have an AB value of 1, 0, and this state could have an AB value of 1, 1. Okay? So I've just simply labeled my states, okay, so I can uniquely describe what's going on in each given state. Okay, what does my actual state machine then look like? And we'll sort of draw a block diagram of what this system looks like. Well, look, I'm going to have some logic here, all right? So I'm going to say, all right, I've got basically, if you like, some kind of block of logic. I've got some inputs coming into that logic. For example, I've got the switch from the pedestrian crossing. I'll call that S. What else have I got? Well, look, I've got the state label, A. Another state label, B. Okay? All right, that's what I've got. Then I've got certain outputs here. What are these outputs? Let's look at them. I've got north, south, let's say green. I've got north, south, yellow. I've got north, south, red. I've got what else? I've got basically my wait light, and I've also got the go light. So you might say, for example, if the switch is 0 and I'm in the 0, 0 condition, now let me just show you, that's going back really to what we might have over, I'll show you over here. Let's put it down here, all right? So in other words, if the switch, let me move that up just a little bit here so you can see that, okay? Now that's visible, okay? So look, if the switch here, this switch were a 0, okay, I'm in the 0, 0 state, so that corresponds maybe to having this is a 0, this is a 0, switch is 0. What do I want going on over here? Yeah, well, I want this light on, I want this off, I want this light on, and this off, okay? You following what I'm saying? Okay. Now, you might argue, if I'm in this condition here with A0, B0, and let's say somebody decides to press the switch, okay? Well, really, what do I want to do next? Well, I still want to have the same light on at the moment. The green light's on and the white light's on, okay, because I'm still in this condition. But when I move into that next state, okay, then I want to change the light conditions. So I need to have some information about where I'm going to go next. And so we actually have 2 more outputs here. And these outputs are called AN for next state and BN for next state. Okay, and that's what we're going to try to work through, and that's what we're going to try to develop a better understanding of. Okay, all right, well, let's finish this. Basically, this A and B value are really provided by two flip-flops. Okay, so we've got our D, Q. Here's the other flip-flop, D, Q, and the output of this flip-flop is the A, and the output of this flip-flop is the B. Now, we feed back next state information into these flip-flops, like so, and like so, okay? And so that's the next state being fed back to the inputs of these flip-flops. Now, the outputs of these flip-flops cannot change until when? Until you get the leading edge of the clock. And then whatever is on D becomes the new outputs of those flip-flops, which are the new AB values coming into this logic, and therefore that will allow these lights then to change. Okay, so what we have in this block is really logic, and from our point of view, these are gates. Okay? All right, now what I want you to do is I want you to think about this a little bit, go back over what I'm saying, and look, we're going to try to develop this a little bit further, and we'll try to do this slowly so that you really can understand what's going on here.